This is section 7.3, part 2. And we're going to now be looking at integrals that involve powers of secant and tangent. Again, we have a little table that kind of gives us a strategy here. You'll notice m is the power on tangent, n is the power on secant. And they tell us what to do if we have an even power on secant, what to do if we have an odd power on tangent, and really this just kind of covers anything else, including the cases where one of them is entirely missing. All right, so let's go ahead and give this a try. On this first one, notice I've got odd powers on both of them, so I would be satisfying the m odd case. And this says split off a secant tangent. Just like before, we're kind of saving that for du. We want to rewrite the remaining powers of tangent in terms of secant, and then our u substitution will be u equals secant x. So let's give that a shot. I'm going to pull off one secant and one tangent. So that's going to make this secant to the 8th of x, tangent to the 4th of x, times secant x, tangent x, dx. I want to write everything in terms of secant, so I'm going to keep the secant to the 8th. But that tangent to the 4th I need to work with. I'm going to go back to my Pythagorean identities here, and I can see that tangent squared would be secant squared minus 1. So this is really tangent squared squared. I'll replace the tangent squared. Well, actually, let me write it out this way for our first time. I'm going to replace this tangent squared with that secant squared minus 1. Like so. And then I'm going to go ahead and use that u substitution that they recommended. Let u be secant x. So if I do that at this stage, if u is secant x, then du will be secant x tangent x, the derivative of secant x, dx, which is exactly what we saved off to the side here. So we're in really good shape. Our integral then becomes u to the 8th times u squared minus 1 to the 2nd power, and then everything here is just the du. All right, just like before, I'm going to have to get that multiplied out before I can integrate it. So let me leave u to the 8th for now. I better square that out first. U to the 4th minus 2u squared plus 1. And then distributing would give me u to the 12th minus 2u to the 10th plus u to the 8th. Simple enough now to just use our power rules. So I'll get 1/13th, and that'll become u to the 13th. I'm just going to go ahead and write it right away as secant to the 13th of x. Minus this one will be 2/11ths. And again, instead of u to the 11th, I'll make that secant to the 11th of x. Plus 1/9, and then that'll become secant to the 9th of x. Plus our constant of integration. And there we go. Let's try another one. All right, so we've got both even powers here. So this is going to put us in the n even case. And this one says split off the secant squared of x. So again, the idea here is that this is what we're going to save for the du. We want to write everything in terms of tangent, and then use u equals tangent x. So we'll do exactly that. We'll split off a secant squared. Actually, yeah, that'll leave a secant squared there. Tangent to the 6th of x. And here's that extra secant squared x dx that I'm kind of saving. We want to write everything in terms of tangent this time. So this is okay, but I need to change that one. So let's see, what have I got? Secant squared is tangent squared plus 1. And then I've still got that tangent to the 6th times secant squared x dx. All right, I think we're ready for our substitution. In this case, the advice was to let u be tangent x. And the derivative of tangent x is secant squared x. Bring the dx over. So that's perfect. That's exactly what we saved, right? We're doing this by design. And then what I end up with is inside my parentheses, that would be u squared plus 1. That's u to the 6th. And then the rest of it's du. So just a distributive law this time. And then I can do my antiderivative. 1/9 u to the 9th, which will actually be tangent to the 9th of x, plus 1/7 tangent to the 7th of x, plus the constant of integration. All right, so those two cases are not too bad, and they're similar enough to the things we've already seen that hopefully those two examples will suffice. What happens, though, when neither of those things is actually present? Then what do? That's the most complicated situation. Basically, anything other than an odd power of secant, an even power of secant, or an odd power of tangent. That actually happens down here in that tangent to the 6th, right? There is no secant at all, but the power here, the m, is even. And I don't have an m even listed over here in my table. I can only do what we've been doing with m odd. So that puts me in this case. In actual fact, to do these kinds of problems, what we need is something called a reduction formula. And I haven't told you about that yet, so what I'm going to actually do is I'm going to skip example 3. I believe it's done in the printed notes, so if you want to see it later, you can. But I'm going to go ahead and talk about the reduction formula first, and then we'll go ahead and do the last example, which uses the reduction formula. It's the same process as this one. So I'm going to go over to the next page instead. Where we talk about that reduction formula. All right, so what is this about a reduction formula? Well, a reduction formula is just a way to reduce the power on a factor in a systematic way. And usually we have to apply that reduction formula multiple times until we finally get to the point where we can do the remaining integral. Here's the one that we need to use in order to use this particular integral. And I keep meaning to get rid of this. I'm going to give you a different form because it's the one we're going to use later. Here's the reduction formula for secant to the n of x dx. It is secant to the n minus 2 of x times tangent of x over n minus 1 plus n minus 2 over n minus 1 times the integral of secant n minus 2 of x dx. Again, the idea here is we need to integrate a power of secant. The formula still contains an integral, but we've literally reduced the power in the new integral. Ultimately, our goal is to get to the point, if we use this enough, that this becomes either secant squared that we know how to integrate, or potentially secant to the first that we know how to integrate as well, just from our basic little list of integrals that we have. So, often have to apply these multiple times. Until the integral becomes doable. All right, let's give this a shot. In example 4, we've got secant to the 5th power of x. And again, I'll have you note that that is, according to our little chart here, power on secant is n. The way we've been doing this works for n even, but I've got an n odd. So I'm in the anything else case, the reduction formula case. All right, so we're going to go ahead and use our reduction formula here. Just start putting it in. We've got an n of 5, right? So I would have secant to the 5 minus 3, or cubed of x, tangent of x, times n minus 1, which would be 4, plus n minus 2 over n minus 1 would be 3 over 4, times the integral of secant to the 3rd power of x dx. Just following this reduction formula. All right, helpful, but not quite where I need to go yet because I don't know how to integrate secant cubed. So I'm going to go ahead and I'm going to redo this whole process. I'm going to say, keep this. This is obviously done. And then I'm going to have 3/4 times, and I'm now going to do another reduction formula, but this time with n of 3. So with an n of 3, that just becomes secant to the 1st, so secant x tangent x, over n minus 1 would be 2, plus n minus 2 over n minus 1, that would be 1 over 2. Integral of secant to the 1st, or just secant x dx. So I think we're finally to the point where we can handle this. Remember from your list of integrals that the 2 types of secant functions we have on our list are secant squared, and then down here secant to the 1st. So once you get down to either secant squared or just secant, we can do the integral. So I've got this one right now, natural log of secant x plus tangent x plus c. So let's see what we've got here. I'm going to write this as 1/4 secant cubed x tangent x. That's going to become 3/8 secant x tangent x. And again here, plus 3/8. And then that integral from the table, the natural log of absolute value secant x plus tangent x plus c. All right, we're going to do one more. The one I didn't do was a bit on the messy side, but the one I'm going to do with you right now is also, and I think doing one messy one is probably punishment enough for us today. So let's go ahead and finish out this section with example 5. I'd like to integrate tangent to the fourth times secant cubed. And again, I'm going to point out to you we are in our unfortunate case here. M would be great if it was odd, but it's not, it's even. N, I would like it if it was even, but it's not, it's odd. So we're in the anything else case. So I want to rewrite the even power of tangent in terms of secant. I want to get everything in terms of secant, and then I want to do reduction formulas. So here we go. Got to get everything in terms of secant. So like we've done before, I'm going to think of this as tangent squared x to the second power. And then I'm going to replace using my Pythagorean identity. Tangent squared is secant squared x minus 1. So we're going to go with secant squared x minus 1 to the second power. Right. Just replacing this tangent squared. Right there. And then times secant cubed x dx. Squaring this out, it's going to give me secant to the fourth x minus 2 secant squared x plus 1 times secant cubed x dx, or secant to the seventh of x minus 2 secant to the fifth of x plus secant cubed x dx. All right, this is where I'm going to drag out those reduction formulas. Now you'll notice I actually have 3 odd powers of secant, so I'm going to sort of have to do this 3 times, but here's my advice. Start with the highest power. In the reduction formula, remember the power on that 7th power is going to get reduced to a 5th power. So do that first, and then you can combine the 5th powers before you go on. Reduce again and combine the 3rd powers before you go on. So I don't want to do this all at once. I want to do it systematically. Okay. All right, so here we go. Right now, I'm working with this first term, an n of 7. Using my reduction formula, let's see if I can put that here where we can see it easily. Let's see here. Actually, oops, I already misstated. I don't need that integral sign. I'm going to use my reduction formula. Let me get rid of that. All right, so the first thing that I'm going to get is reducing. I'm going to get the n equals 7, so secant to the 5th x, tangent x, over n minus 1, which would be 6, plus 5 over 6, integral of secant to the 5th x. It says dx right there, but I'm actually going to sneak something in here. I also have a minus 2 secant to the 5th, so I'm going to put those together. Oh, you know what? I'm sorry. I can't do that because of that 5/6. I'm getting ahead of myself here. Let's go ahead and leave that one the way it is. And then I've got minus, and I've got 2 times the integral of secant to the 5th x dx, and then plus the integral of secant cubed x dx. Sorry about that. I almost made an arithmetic mistake there, but fortunately we caught it, right? All right. So let's see what we've got. We've got secant to the 5th of x, tangent of x, over 6. And then the 5/6 minus 2 would be a negative 7/6. Integral of secant to the 5th x dx, plus our integral of secant cubed x dx. All right, next I'm going to use our reduction formula again. This time we have an n of 5. So I'm going to write that as 1/6 secant to the 5th x tangent x minus 7/6 times. Here we go, reduction formula with n of 5. Secant cubed x tangent x over 4 plus 3/4 integral of secant cubed x dx. And then I still have this plus the integral of secant cubed x dx. All right, 1/6 secant to the 5th x tangent x minus 7/24 secant cubed x tangent x. And then let's do a little bit of mental arithmetic here. This is going to be a negative 21 over 24. Put this off to the side. In front of the secant cubed integral. And then I've got a plus 1, which could be 24/24. So it looks like I have 3/24 times that secant cubed integral. Just 3/24, sorry about that. Double checking here, negative 21 over 24 looks good, plus the 1. All right, last time for my reduction formula. Sorry about that. And here we go for, again, the last time with the reduction. This time we've got an n of 3. So we're going to have secant to the 1st, so just secant x tangent x, over 2, plus 1 over 2, integral of just secant x dx. All right, almost there. This will become a 3/48 secant x tangent x. This will also become a plus 3/48. And there's that same integral of secant x. Just a reminder again, that's on our list. It's the natural log of secant x plus tangent x. Plus c. There in all its glory is our final answer. Not beautiful. These usually aren't. They're long and they're kind of a pain in the neck, as promised from the beginning, right? But this is how reduction formulas work. Just a couple notes at the bottom of the page and then we'll be done here. First note, there are actually other reduction formulas, especially for trig functions, but others too. And we will get to them actually at about section 7.6, I think it is, in this chapter, when we integrate using tables. We're introducing this reduction formula right now because it would be so much work to complete secant and tangent integrals without it. But we'll see some more. This is not a one and done kind of a thing. Finally, the other note, and I mentioned this early on, the techniques that you used to integrate powers of cotangent and cosecant are almost identical to the ones for secant and tangent. Basically, you just have to watch out for the negative signs, but other than that, they look the same. So I'm not going to treat those integrals explicitly here, and I won't ask you about them on tests or anything. Okay. All right, that brings us to the end of section 7.3.